All right. So the limit of a sub n plus 1 over a, this a sub n plus 1 should be here. As n approaches infinity, it's the limit up there. Now for that, you can use the trick that we do, okay? You can simply, for example, divide first fraction everything by 2 to the n. So we get 1 plus 10 divided by 2 to the n, 2 plus 10 divided by 2 to the n, and then 4 divided by 3 to the n minus 3, and then 4 divided by 3 to the n minus 1. Right? Now as it goes approaches infinity, you can see a bunch of zeros showing up. Right? For example, that goes to 0, goes to 0, 0, that goes to 0. So you're left with half times 3, because you have negative 3 over negative 1, which is 3. So your final limit is 3 over 2. Bigger than 1, so the sum of, say, a sub n. So by ratio test, diverges. Question on that? You are. Anybody else has question on 10.5? Okay. So let's go back to 10.4. Okay. So 10.4 is comparison and limit comparison. In my experience, and in terms of frequency, it's a less frequent used test comparing, for example, with integral or even ratio and root test. Ratio and root test, I think it's the most frequent used test in testing series in convergency or divergency. But there are some series, that for which through ratio and root test fails, okay, or it's inconclusive. So comparison is a good one. Let me start with this example. For example, for something like this, n squared plus 5 over n cubed minus 7n. As n approaches from doesn't matter, from 1 to infinity. If you set up, so here a sub n is n squared plus 5 over n cubed minus 7n. Feel free to set up ratio. So you see, we can check that the ratio test and the limit of root test are both equal 1, meaning they are inconclusive, right? Doesn't tell us if it diverges or converges. These two tests as an approach to infinity. I mean, someone might say, We can do integral test. That's true. Okay. So integral test can be used by simply integrate 1 to infinity x squared plus 5. And what else? X cubed minus 7x, okay? Dx. So find the value of this integral, then the value of that series is going to be the same. If this diverges, the sigma, the summation diverges as well. And same thing for convergence. But another useful test here would be comparison, okay? And the name, says enough. You comparing this, the given series with the behavior of some series that you already know. So that's that's one, negative fact about it, or, that's one of the cons basically about this test, is that you are required to know already the behavior of a lot of series. It's like, let's say a series is given. Let's say this guy is given, okay? And you want to do comparison. That means it's like you already have a big pot, right? You already know about a big collection of series and you know the behavior of them, so that you can go grab one of them and then compare this guy. So let's say you grab one called sigma b sub n and you compare this with this guy. But that requires, your knowledge of behavior, a lot of series. Okay. So that's why I talked about ratio and root test, so you can see more series and then come back, do comparison. Okay. Let me write down how it works. So theorem. Let me see what notation they're using. Limit comparison. Comparison. Okay. So let sigma a sub n be a series with non-negative terms, meaning all a sub n's are bigger than or equal 0. And let b sub n be another series also with non-negative terms. Non-negative terms. Same thing, b sub n bigger than or equal 0. Okay, part 1 of this theorem. If b sub n is less than or equal a sub n for all n, not for all n, for all n bigger than or equal some integer n. Basically, it doesn't have to be true for, for example, n could start from 7. That means we don't need to have this relationship, this inequality for b naught, b1, b2, all the way through b sub 6 with a naught, a1 and a sub 6. Like we could have this. It doesn't matter. But what matters is that after index 7, all the bn's are less than or equal A sub n, okay? Basically, the first few terms, they're not gonna affect the behavior of a series. That's the meaning of this statement. So if that happens, if B sub n is less than or equal to sigma phi, and this sigma an converges, then sigma bn converges as well. 2, if sigma bn diverges, then sigma an diverges too. Let me explain this. I could have stated it in a shorter, statement. Okay. Let's say this guy is given and you are asked to check the behavior if it converges or diverges. Okay. All right. So this is given and it's unknown behavior. Unknown behavior. We don't know yet. Okay. But we are able to find another series. So if we can find another series for which we know the behavior, okay, let's say sigma b sub n, and we figure that a sub n is less than or equal b sub n, okay, and also we know sigma b sub n converges. Okay, first of all, if that's true, right, if a sub n is less than or equal b sub n, then it can take sum and we would have this. Okay, now what's the condition? We already know b sub n converges. Sigma b sub n converges. That means the summation is a finite value, right? And since the terms are all non-negative, that means this sum is bigger than or equal to 0. Well, you have a number that is bounded by 0 and a finite value. So what's the conclusion about the unknown series that we started off with? Do you think it converges or diverges? It converges. Why is that? Well, it's obvious because, it is less than equal a series that we know, like this one is bigger. It's bigger than that guy, and it converges. So of course this is going to converge. So that's basically how you compare it with another series, and then you conclude if it converges or not. The other way around. So the thing is, if you want to show that it converges, if you want to show that this thing converges, you're going to have to find a bigger one that it converges. So that's the hard part. Let me repeat it again. You sort of guess that this guy converges, okay? If you want to show it converges, you're going to have to find another series which is bigger already, and that one converges. So it can conclude, of course, the smaller one converges as well. Now, for the divergency is the opposite. So let's say a sub n is bigger than or equal to b sub n, okay? So that's the unknown one. You find this, right? That's the one you get help from, right? That's the helping one. And you realize, and sigma b sub n diverges. Well, diverges, that means either it doesn't exist or the sum is infinity. And the sum of a sub n is bigger than or equal to that guy. So of course this guy is going to diverge. Make sense? Okay. Let's start with a few, simple examples. Example. Let's do this one. Let's do 1 over n squared plus 5. And it's starting from 0 to infinity. In fact, I'll tell you a trick later. That in case of rational functions, like this guy is a rational function, right? You have a polynomial divided by another polynomial. And we can easily find this series we can compare that. Okay. First of all, here's the thing. You sort of have to guess to see if series diverges or converges. So do you guys think it converges or diverges? Diverges. Let's see. What's the most obvious series that we can compare this guy with? You can open your mic and say it. What's the most obvious? Exactly, that's 1 over n squared. Because 5 at infinity comparing with n squared is nothing, literally nothing, right? So at infinity, 1 over n squared plus 5 is very similar basically to 1 over n squared. Okay? So we can go ahead and compare it with this guy. And here's how we do it. First of all, so this is a sequence of algebra, okay? Let me erase that part. Same thing. I want to write statement, and you guys tell me if it's correct or not correct. So I claim n squared plus 5 is bigger than n squared for all n bigger than equals 0. Is that correct? Yeah. Because, n squared and n squared is the same. You add an extra 5 units to the left side. So, of course, it's always bigger. Now, go ahead and reciprocate them. Right? It's like you have 7 bigger than equal 3, and if you reciprocate them, you get 1/7 and you get 1/3. Except when you reciprocate, what happens to the inequality sign? Does it stay the same or changes? Flips. So we're going to do the same thing here. And why are we doing that? Well, start with the first step of an algebraic expression or inequality, which is this guy. Like we already accept this. We know this. This is true. Now manipulate it until you get to this guy. Okay? So what do we have to do? Well, if we reciprocate it, we get to that guy. So 1 over n squared plus 5 is less than equal 1 over n squared. Right? And then take sum on both sides. So you get sum of 1 over n squared plus 5 is less than sum of 1 over n squared. And starting from, let's start the series from 1 so we don't have to deal with dividing by 0. So 1, even here 1, 1 to infinity, 1 to infinity. Okay, now that's the series that we are comparing the original series with. So we need to know the behavior of this guy. What do we know about this guy? Does it converge or diverge? It converges. Why? It is correct. You have to justify. Yep, it's a P series with P equal 2 bigger than 1, so it converges, right? So we already know this one is a P series with P equal 2 bigger than 1, so converges. Now, by comparison test, this smaller series converges as well. And that will be it. Okay. And you can do the same thing for divergency. Let's do one for divergency. I'm gonna write down one that also can be, proved diverges using integral test. Okay, but we can use simply, again, comparison test. So let's do 1 over n minus 3, and let n start from 4. How about that? To infinity. Okay. All right. Again, you can do integral test, right? 4 to infinity, 1 over x minus 3 dx. Find that, and then the value of that one is the same. Okay. But now let's see how integral comparison test is going to help us to show if it converges, diverges. Okay. Again, this is what you're going to ask yourself. What's the most obvious series you're comparing this with? Yep, it's sigma 1 over n. It's very similar to sigma 1 over n. Okay. And again, this is how you start. We know n minus 3 is less than n. Do you agree on that? For n bigger than or equal 4. And now go ahead and reciprocate them. So we get 1 over n minus 3 is bigger than. Oops, not sum now. It's 1 over n. Now sum them up. Is bigger than sum of 1 over n, and it's starting from 4 to infinity. Okay. So we are able to compare with the series. It's bigger, right? So we know this guy diverges. Again, p series. P equal 1. So that by comparison test, diverges as well. Okay. So any questions on that? I want to look for some non-trivial examples. Let's see. Actually, let me state. So this is very situational. Also, it doesn't matter what the series starts at. You just have to make sure it doesn't make an undefined case. But no, it doesn't matter. Okay, because even if the first few terms doesn't satisfy the inequality, you can still make the judgment. Remember, the first few terms, that means you're only talking about a few finite values. Because even if it's 10 terms, you have 10 numbers. The sum of 10 numbers is a finite number. Okay, whereas when you approach infinity, you're dealing with infinity. So. But no, it doesn't matter what the series starts at. Let me state the other theorem. This one is called limit comparison. Okay. I think it's easier to use. At least you don't have to prove the sequence of algebra. Like you don't have to, justify the inequality by writing down the sequence of algebra. As long as you identify the series you want to compare the original with, all you have to do, you take a limit, and then you make your judgment. So this is how it works. Theorem. So that one was comparison. This is limit comparison. Basically, again, name is self-explanatory. You're comparing it using a limit, and I'll explain how it works. So it's a limit comparison. Okay. So consider, I'm gonna write it in a very minimized statement. So consider, let's consider two series. Consider two series, sigma an and b sub n. Okay. And let L be the limit let me see. Does it have to be bigger than 1 or less than 1? No, as long as it's non-zero. Let me make sure. Yes. So let L be the limit of a sub n over b sub n. And actually, this ratio doesn't matter. It could be b sub n over b a sub n, doesn't matter. And starting infinity. Okay. And let's make this absolute value in case you have some negative terms. Let L be this guy. So of course, you know L is bigger than or equal 0. Now, if this L is non-zero, so if it's strictly bigger than 0, okay, this only works if that L is non-zero. Even if it's 1 over a million, still this test works. If this happens, then sigma an and sigma bn have the same behavior. Let me mention that if L equals 0, the test is inconclusive. Okay, what does it mean? Example. So let's say if the limit of an over bn, n going infinity, let's say it's 0.7. I don't care what number it is, as long as it's a non-zero positive number, it's bigger than 0. Okay, if that happens, and if we already know, let's say sigma bn diverges. Now, what's your conclusion about sigma a sub n, according to the theorem, since they both have the same behavior? Diverges. Right? That's what the theorem says. It says, set up this ratio, take limit. If the limit is bigger than 0, strictly bigger than 0, then both series have the same behavior. So let's say this was given to you. So this was initially unknown. Okay? Then you get help from this guy. So you come up with this series, you set up that ratio, you take limit, and it's non-zero. And you know this guy diverges. Then your conclusion is sigma a sub n diverges too. So for this test, you don't have to do the sequence of algebra showing is less than equal or bigger than equal. Just a normal comparison. Okay. So, let's go back to the two that we just did. Okay. In fact, let's do the initial one that we talked about. Or, let me just quickly mention these two. So for 1 over n squared plus 5, you're comparing this with 1 over n squared, right? If you do the limit comparison, you do this limit. 1 over n square, 1 over n square plus 5. And it doesn't matter. You could do limit of 1 over n square plus 5, 1 over n square, right? For example, if this limit, for example, if it's half, this one would be 2. But they're both bigger than 0. It doesn't matter. Okay. So let's find one of the limits. Let's find, the left one. As n goes to infinity. So this is the limit. Let's simplify to get n squared plus 5 over n squared. And then you know how to take limit of that, right? Either you do L'Hopital's twice, or let's divide everything by n squared. So we get 1 plus 5 over n squared. 1. That's 0, so it's 1. 1 is bigger than 0. So this one and this one behave the same. But we know this guy converges. So this guy converges as well. Okay. Now, that was p equal to series bigger than 1, so that's why it converges. Okay. Let's talk about the less obvious question. Let's do I want to do 1 part C. It's this one. And it's starting from 3 to infinity. Okay. And we want to do comparison or limit comparison, okay? What do you want to compare this to? What series? Remember, you have to think about infinity. So at infinity, what's the closest series having behavior close to this one? You can simply ignore 5. As soon as you ignore 5, you can figure out what series you have to. Nice, it's 1 over n. So it's comparable to that guy. If this 5 was 5n, it still would be the same. Think about it. Basically, in numerator and denominator, you pick the biggest term for large n values at infinity. Okay? Well, let's go ahead and do. By the way, what do we know about this series? We already know that one diverges P series, right? So P series, P equal 1 diverges. Now, by limit comparison, again, it doesn't matter which one you put on top and bottom. So the limit of 1 over n over n square minus 5 divided by n over, what am I doing? N over n square minus 5 and approaching infinity. And so if you multiply by the reciprocal, you'll see it's going to be n square minus 5 divided by n square and approaching infinity. And you know the rest, right? So it's 1 minus 5 over n square, 1, n going infinity. That's 0. So the limit is 1, bigger than 0, same behavior, so that this one, what was it, 3 to infinity, diverges. Okay. So I'm going to write down series. You have already seen similar. Did I give you this one in the quiz? A similar one? So this is 1f. And they're using P. I'm going to just use N. And it's starting from 3 to infinity. Okay. So we want to compare this with a series that we have already seen before. At least, we can find the behavior. You saw it in integral test section. What was it, 10.3? So what series do you want to compare this with? I mean, think about it. Natural log of n is already natural log of n, okay? So you want to keep it as it is, at infinity. Yeah, it's that one. But n minus 2, you can ignore 2 and then simply compare it with n itself. So this series you want to compare this with is the sum of 1 over n natural log of n, and starting from 3 to infinity. Okay? Now this one, we have already talked about this in 10.3. I think I did that example. It diverges by, so we know this guy diverges by integral test, right? Which was, just simply integrate 1 over x, natural log of x, dx, 3 to infinity, and the antiderivative of that is natural log of x. And then you evaluate it from 3 to infinity, it's natural log of infinity, that's infinity, so that's why it diverges. So since integral diverges, this series diverges as well. So we know this guy already diverges. And according to the argument we made here, it's comparable, right? All we have to do, let's go ahead and set up the limit comparison test. So the limit of 1 over, n minus 2, natural log of n, 1 over n, natural log of n, as n approaches infinity. The natural log n part cancels out, right? So you're left with simply limit of n over n minus 2 as n approaches infinity. And that's 1, bigger than 0. So they have the same behavior. We already know this guy diverges, so by limit comparison, sum of 1 over n minus 2 natural log of n, and from 3 to infinity diverges too. Okay. Now, why were we able to compare this? Well, because we have already seen this before, right? Or we were able to, show that one converges, diverges by some other test that we already established. Let me write down a few examples, and you guys just tell me what series you want to compare it with, and I'll leave the rest for you. And these are, again, book questions. So the sum of n over n squared plus 4n plus 11. What do you compare this with? The next one is sum of, well, let's do it this way. 2 to the n over 3 to the n plus 5. What do you compare this one with? Sum of let n start from 1 here to infinity. Let it 0 to infinity here. What else? Oh, this is a good one. 3 to the n to the 10th plus 5 to the n starting from 0 to infinity. Okay, let's start with the first one. What do you compare the first one with? Nice. Again, at infinity, for denominator, 11 and 4n is ignorable, is not comparable with the how fast n square grows, right? For large n values. So basically, you compare the denominator by n square, numerator itself, it's n over n square, so you end up with 1 over n. Okay? And you can do limit comparison. This one diverges. The original one diverges as well. All right, second one. What do you compare the second one with? Remember, you can open your mic and instead of typing it. So what do you compare the second one with? It's 2 to the n over 3 to the n. Nice. Ignore 5 again, right? So on each numerator and denominator, figure out which term is ignorable and completely ignore it. Basically, find the bigger term and ignore the other one, and ignore the rest. So this one is comparable with 2/3 to the n and is starting from 0 to infinity. Right? So you can set up the limit. And by the way, what do we know about this guy? Does it converge or diverge? And you have to tell me why. It converges because it's geometric with a ratio less than 1. Absolutely. And you'll see this one converges. The left one, the original one, converges as well. Okay. How about the last one? What do you compare that one with? So, of course, for the numerator, you go with 3 to the n. In denominator, you have the power function n to the 10th. In fact, let me go ahead and write it as n to the 100. How about that? It's a power function, and the other one is exponential. Beautiful. So you ignore the power function. Again, comparing power to the exponential grows faster. So you can simply compare that to 3 to the nth over 5 to the n. And again, this one converges because it's a geometric ratio less than 1. Okay? So, this is not something that's taught, is not teachable, but knowing the behavior, of all those functions that we talked about, natural log, power, exponential, factorial, and so on, you can compare them like that. Okay. Any questions? So you should be able to do 10.4 now. And actually, I'm going faster than schedule, interestingly enough. So feel free, guys, pause, stop me, ask questions. On Thursday, feel free to bring questions and we can work on questions. So is the last one just the geometric series? Yes. Yeah, the last one is, 3/5 to the end again. So this one is geometric ratio less than 1. So this one converges. This one converges. So that the original one converges, but this one diverges. quiz will be covering 10.3, 4, and 5. Correct. I could have started 10.6, but I think it's going to be too much for you guys. I mean, it's already a lot. But those 3 sections, I can make a long quiz. So work on the problems. Bring questions on Thursday. On Thursday, I'll just plan to do more and more problems. Okay? Any questions? Concerns? I'm gonna go ahead and stop the session.